Hello everyone, my name is Leszek Pawlowicz. I'm an associate practitioner in the Department of Anthropology, Northern Arizona University, Flagstaff, Arizona. And this is an extended video version of a talk I gave at the 2015 Society for American Archaeology Conference in San Francisco, titled "A Documentation of Lithic Artifacts Using an Inexpensive Reflectance Transformation Imaging System." And the reason I say extended is because I was forced to cut a few slides and a few demonstrations because of time limitations, and I've put some of those back into this particular version. So I'm going to start out with a really basic question. Given that digital cameras and digital photography is in a very advanced state these days, why is it that manual illustration, meaning line drawings, are still being used to document lithic artifacts? There's a number of reasons you can come up with. I'm going to give a few here, and you can probably come up with a few of your own. First one is tradition. It's been used for decades for documenting lithic artifacts, and I'm not saying that in a pejorative sense. There are certain conventions used in drawing that are well known and make it easy to interpret these drawings. The second reason I'll give is cultural restrictions. There are certain artifacts that are not allowed to be photographed, but can be documented using drawings. Another reason that I've seen given is that manual illustration allows the archaeologist and the illustrator to highlight key man-made features and remove distracting features. Not sure I'm crazy about this one. It's, who's to say that a distracting or unneeded feature now might turn out to be an important one at some point in the future. And often these drawings are the only documentation that a particular lithic artifact will get. Finally, I think probably the biggest reason is that making a good digital image of a lithic artifact can be really, really hard. You have issues of low relief of the surface features and low contrast as well. The material coloring or texture can be non-uniform, making it difficult to make out surface features. And then finally, quite often, the material can have a shiny or specular surface. I'm thinking of obsidian as a prime example, but chalcedonies and chert can also suffer from this as well too. Here's a couple of images from the archaeological illustrator Lance Trask that show this. On the left are Lance's photographs, which are actually pretty good in my opinion, and on the right are his freehand drawings of the same artifact. You can say that the photographs are more realistic, but it's difficult to argue that you don't see far more details in the drawings than you do in the actual photographs themselves. And those are for some of the reasons that I just mentioned. Some of the material can be glossy, or there are issues with contrast. It's just difficult to see them in a photograph. So people have been looking at 3D digital alternatives to photography, mainly involving making full 3D models of lithic artifacts. I'm going to give a few references here. There's a technique called microcomputed tomography, or micro-CT, which is essentially making a CAT scan of a lithic artifact, and that generates a full 3D model that can be manipulated in a computer. 3D photogrammetry, also called structure for motion, where you take photographs of an artifact from many different angles and put those into a computer program that generates a 3D model based on the differing viewing angles of every photograph. And finally, there's laser scanning and structured white light scanning, which can also be used to generate a full 3D model. I give a reference to a paper by Matt Mignani in Advances in Archaeological Practice, not necessarily because he's the first person to do it, because he's not, but rather because it's a good general summary of 3D imaging of lithic artifacts, and also a very good comparison of using laser scanning versus 3D photogrammetry. So I've been looking at another digital imaging technique called Reflectance Transformation Imaging, or RTI for short. Originally was called Polynomial Texture Mapping, PTM for short, and you may still see it referred to as that in the literature. Technique was developed by Tom Mulsbender and Dan Gelb of Hewlett-Packard Labs back in 2001. I first stumbled across it in 2009 and thought, wow, this would be a really great way to image lithic artifacts. Wasn't an original thought even then, and since then I've seen a number of photographs up on the web showing people using it for exactly that purpose. So how does it work? You take digital photographs of an object, an artifact, from a fixed camera position with different lighting angles for every photograph, but a constant lighting distance. You then take all those photos and put into software that analyzes them and fits an independent light intensity equation as a function of the lighting angle for every single pixel in that image. The final result is a virtually relightable model of the object. Now, what does that mean? So here is a modern point made of black obsidian. I believe this is Lookout Mountain obsidian from California. Typical example of a difficult material to photograph because the black makes contrast iffy, and it's also very, very shiny, so you get lots of specular highlights in the photographs. This particular image is taken from the standard photographic lighting angle from the upper left, but is one of a series of 48 photos of the same object, each photo taken from a different lighting angle. And I can show that to you a different way by basically cycling through every single one of the photographs, or most of the photographs. So basically, you're just changing the lighting angle and taking a photograph at every single different lighting angle. You then take all those photos and load them into a program that creates an RTI data file, which you can then load it into the viewer program, and you get a view that looks like this. And the first thing you can notice is that all those glossy specular highlights have disappeared, because those are just single, offset points on the lighting curve, and the process of fitting a lighting curve basically smooths those out. And in the upper right, there is a lighting control, and by clicking and dragging the lighting control, you change the virtual lighting direction. And so that's what's meant by a virtually relightable model of the object. And because it's digital, you can also use a number of different viewing modes that basically modify the behavior of the lighting curves to even more greatly exaggerate the effects of changing the lighting curve. You can also go and sharpen up the image and zoom in, like so, and then move the lighting angle and just basically look for very, very subtle details in the surface. So you can see things with this technique that are certainly not visible in, or most likely not visible in a single photograph, and you have basically the effect of being able to choose the exact lighting angle that brings up the details that you're interested in looking at. So how do you get these photos? Well, there's a number of different ways to generate an RTI data set. Here's one example using a technique called Highlight RTI. So in this technique, you have an individual who has a light and moves the light to different angles relative to the object being photographed down here. The string is used to maintain a constant distance between the object being photographed and the light, and also to make sure that the light is being pointed directly at the object. You have a camera directly overhead pointed down at the object. And then right next to the object are two black reflective spheres. And these show up in every single photograph, and along with a highlight generated by the light that is being used to illuminate the object. And you can use the highlight in these black spheres to determine what angle the light was at when the photograph was taken. The system certainly works. I did a few experiments with it and got usable results. But more often than not, I would bump into either the camera or the tripod, screw up the alignment, and have to start all over again. So I decided that this wasn't really a method that I was interested in using for documenting lithic artifacts. The other main technique used in RTI is what's called dome RTI. And in this one, you've got a half sphere, a dome, that has lights, typically LEDs on the inside, and there's a camera at the top looking through a hole down at the artifact, which is hidden by the dome here, but is sitting basically directly below the apex of the dome. Now the LEDs are turned on and off sequentially, and the camera is fired in sync with the lights. Usually there's an electronic control system that will handle all that work for you. Because the LEDs are fixed in place, the lighting angles are fixed, and the distance of the light to the artifact is also fixed at a constant value. The system can be operated by just one person versus 2 or even 3 people that are sometimes required for a Light Rti. The data acquisition and processing times are substantially less than with Light Rti. But the biggest issue is cost here. When I researched dome RTI systems, I found that there were no commercial systems available. And I also found that there were custom systems being built, but the rough price range I was seeing was in the range of $10,000 to $30,000 for a system, which is well out of my price range. So I decided that I would design and build my own system. And here it is, the first system, the Mark I AAA, although you can throw a few more A's on there. And that's because the system has been rebuilt on multiple occasions. There's been 3 different lighting systems, 2 different controllers, 2 different camera stands, and so on. But this is the final version. It's an 18-inch diameter dome with an electronic control box down here. Sitting on a stand, the artifacts are slid in underneath and raised into position on the lab jack. System works really well. I have no complaints with the overall results. The problem I have is that the size and the bulk and the complexity of all the parts together mean that it's very cumbersome to take the system off to the locations where the artifacts are. And it's also a lot larger than what I need. I mean, an 18-inch system is capable of imaging artifacts of, say, 4.5 to 6 inches in maximum diameter without problems. And most of the artifacts that I'm looking at are in the range of about 3 inches or less. So using all the experience I got building this first system, I built the Dome Mark II. And this one has 48 high-power 3-watt LEDs on the inside of the dome. It's got a synchronized electronic control box that fires the LEDs on and off and also fires the camera on and off. This is set up right now with a high-end Canon point-and-shoot, but it will work with most modern digital SLR cameras. Data acquisition time is 1 to 3 minutes, depending on how fast the camera works, and data processing time, once you get the photographs off of the camera into the computer, is also on the order of about 1 to 3 minutes. It's a one-person operation. You basically stick an artifact in, push a button, get a set of photographs, take the artifact out, put another one in, push another button. Very easy. Total cost of the system, including the camera, was well under $800. And I think it's a little bit better than $10,000 to $30,000. The dome diameter is smaller, 12 inches versus 18 inches for the other one. And the stand that it's sitting on is a 13.5 inch by 13.5 inch. You can get good results on anything less than 3 inches and acceptable results up to about 4 inches in maximum artifact length. Uses either a plug-in DC power supply or a battery pack, and the total weight of the dome, the stand, the camera, the controller, everything together is less than 4 kilograms. And the reason I highlight that is because this system is actually fully portable. The backpack here contains the dome, the stand, the camera, the controller, all parts needed to run it, plus room to spare. And the total weight is less than 5 kilograms. And this makes this a fully portable, field-ready system. So if you're going to a field site, we are not allowed to collect lithic artifacts and bring them back to the lab for documentation. You can use this system to do a full and complete documentation of the artifact at the site. You can also reconfigure the system to work with either a USB microscope or a digital SLR with a macro lens to get high magnification imagery, and that's very useful for looking at wear patterns on lithics. And then finally, you can also modify it so the dome is in a perpendicular sense and use it in an upright mode with larger artifacts, say for example pots or other larger objects. And I can run the video here showing the lights going on and off in sequence, and the camera is sitting there. This is running a little bit faster than it would in real time. So, yeah, it's all great, but I can't put an RTI digital file in my next paper. and that's true. This is great for interactive viewing of the object and seeing details by changing the lighting angle, but you can't do that with a single still photograph. And even with RTI's ability to set that arbitrary lighting angle, there's no guarantee you'll find a single lighting angle that shows every important detail in a single screen capture. And that's true, actually, for any of the other 3D lithic documentation techniques. You still have to find the proper lighting angle to show things, and you're not necessarily going to be able to see everything clearly. RTI viewing software has multi-lighting modes, but results on lithics are usually unsatisfactory, and I can show you a couple of examples of that right now. So let's zoom out here. There is in the RTI viewer a mode called static multi-light, and the idea here is that it analyzes the object and the surface topography and tries to combine multiple lighting angles to give you the best result. And let me click on that, and you get something that looks like this. This isn't actually half bad, although you are losing quite a bit of detail up at the top and on the left-hand side. You can play around a little bit with some of the settings to try and improve that. I found in general that I'm not usually happy with the results that I get with this particular technique, and quite often you can also get odd lighting artifacts out of it. So there's another viewer called the Inscript effect viewer that gives you the option of basically creating not one but two virtual light sources and moving those independently. And so I can move this one over to here, and then I can go to the other one. I can position it over here and so on, and try and find some combination of lighting angles that gives good results. And what you see here is you're getting good results over most of the artifact, but down at the base you're not really getting a lot of light on there, and so you're missing a lot of the critical details that would show up with different lighting angles. So I play with this on occasion. Sometimes I can get acceptable results. More often than not, once again, I don't really get good results with this. So what are the other solutions? Normals mode. In RTI, you get a light curve, and the angle at which the light intensity is at its highest corresponds to the perpendicular direction to the light at that particular point. And in RTI normals mode, the viewer color codes the pixels based on that perpendicular or normal direction. The picture here is a sphere that's been imaged using that normals mode, where if you take a look on the right-hand side, the further off to the right you get, the redder it gets. Red is, and then as you go over to the left-hand side, red becomes less pronounced. Green is higher in the in this up direction this way, and then less down this way. And then blue is at a maximum pointed directly out of the screen and at a minimum pointed directly into the screen. So here's an example of using that on the Molina Spring Clovis. This is a Clovis point from the Apache Sitgreaves National Forest in Arizona. And this guy is really, really tough to image. It's made of a light mottled glossy shirt, and the flake scars are very, very difficult to see, even by eye. Now you can take that and do basically a standard, let's close this. Look at it using the standard RTI viewer and move the lighting around, and you can see, yeah, sometimes you can, in one direction you can pick out some of the flake scars, but other ones don't show up, and difficult to find a satisfactory angle for that. However, if you go to the normals visualization mode, you can now you're basically looking not at the actual image details, but rather at the surface topography converted into different colors. And now flake scar data that was not visible in the normal view pops immediately into view. So let's go here, and that's the normals mode. Now if you take that and run it through some standard image enhancement techniques or some custom filters that I've designed using the program MATLAB, you wind up with an image that looks like this. And now all of the flake scars are very, very clearly visible in this. And once you have it, the normals image, and this is representing surface topography, not details, you can do a variety of different kind of filters on it. I've designed a couple of custom filters that will go in and look at different aspects of the surface to pick out different details. Now here's a few more tough material types to image. I've got a Chalcedony here. It's glossy. There's not a lot of surface contrast. It's difficult to pick up stuff. There's that glossy black obsidian point from before. And then finally, there's a piece of obsidian that's not just specular or shiny, but is also transparent. And if you don't believe it's transparent, there's a view of it looking at my window. If you run it through the same process with normals and enhancement, you wind up getting images that show the surface details much more clearly. And I think that these images, in terms of the detail that they show, are at least equivalent to, if not better than, any line drawing that you could make of any of these points. But even if you prefer line drawings, you have the option of taking one of these images and loading it into a program like Photoshop or Illustrator, and then using it as a background to make a hyper-accurate tracing of surface details that will be much more accurate than any freehand drawing that you could make of any of these points. So, RTI and 3D. So I mentioned before that there are numbers of 3D characterization techniques like micro-CT and photogrammetry that create full 3D models of an artifact. RTI can't do that because you're basically just shooting a single side of the object, and so you can't see the whole thing in a full 360-degree view. But what you can do is you can derive 3D surface information from the normals data, from the perpendiculars at every single point on that object, and use that to create a 3D surface. Now, I just got this working a few weeks ago, and I'm working on resolving errors and inaccuracies, but I can already get useful information and visualizations already from what I've got. So let me show you an example of that. Here's a 3D model of a Clovis point from Upaki National Monument in Arizona, and this is a fully rotatable 3D object. One side only, so you can see it's hollow on the back side. And you can modify the lighting direction. You can also go in and modify the way that the light interacts with the surface to give a variety of different appearances to this thing. This is a kind of a shinier appearance. This is this one here is supposed to mimic a electron microscope type shading. There's also a shader here in this program. It's a free program called MeshLab, by the way, called radiance scaling. And what that does is it shades the surface based on whether or not it's convex or concave. And that can pull up interesting details and information that isn't visible any other way. So I'm continuing to look at different ways to use this 3D information to go and extract more information out of all these objects. Now, while I've mainly looked at lithic artifacts using RTI, I just wanted to spend a few minutes showing some examples of other artifact types common in the US Southwest that can also benefit from RTI imaging. This is a piece of corrugated pottery, 2CN corrugated to be precise, from northern Arizona. And by modifying the lighting angle, you can pull up various details, and you can see the fingerprint impressions are starting to show up quite nicely in some of these corrugations at different lighting angles, whereas they don't show up necessarily all that well when the lighting is from overhead. And you can also sharpen things up in a number of different ways. And let's crank that up. And so really do a very nice job of bringing out very clear details on this piece of pottery. So here's another piece of corrugated pottery, also from the Southwest. Also a variety, I believe this is a variety of two-seam corrugated. And you can do the same thing with this one. Let's zoom in a little bit here. And you can see there are fingerprint impressions that show up, not just in the corrugations in this case, but also more complete ones that are showing up on the rim of this shirt as well too. This is a piece of Pinedale Polychrome from eastern Arizona. It's mineral paint, so it's very thick and doesn't sink into the surface during the firing process. And what you can do with this is use a technique called Specular Enhancement that gives a shiny appearance to the surface. And let's zoom in here, and you can see very clearly details about how the paint was laid down on this pot. And you can see things like, for example, it's very clear that there are little touch-up marks here used to join up design features that don't show up all that clearly when the lighting is from directly overhead. And you also see that in the normals visualization mode as well too. The little blobs here are clearly at a higher in topography than the rest of the painted features. So here's a basket from a Basket Maker 3 cave in northeastern Arizona, and just by using the changes in the lighting angle, details that aren't immediately obvious pop up, like wear patterns on the basket, and you can sharpen those up as well too to see them more clearly. Just a nice way to look at fiber materials. Here's a bone awl, also from northeastern Arizona, and you can look at it a variety of different ways to try and see details like surface wear patterns. Here's a sandstone mono, a grinding stone, also from northeastern Arizona. Not a lot of detail visible on it from this particular lighting angle, but if we go to the specular mode, and let's knock that down a little bit, you can see all of a sudden the pecking marks used to rejuvenate the surface immediately become obvious, whereas they weren't all that obvious in the original photograph. Here's a bighorn sheep effigy bead. It's about 1.4 centimeters in size, and you can do the same things as well too. You can basically go in and change the lighting angle and see details about how it was actually fabricated. Let's go in here. So this is a Saloon Token from the Sedona area. Basically, you'd use this instead of money at a saloon in Prescott, Arizona. Kind of corroded, rusty. It's originally aluminum. And if you go to specular mode, go to normals mode, details that aren't easily visible in the photographic view are immediately visible. And in specular mode, you can also take a close look at image details. But finally, and most importantly for archaeologists, this technique is absolutely killer for fossils. And yes, it's a joke. All right, so for more information on RTI, there's a couple of good sources. The Cultural Heritage Imaging website is a great source of information about RTI. There are links to free software developed by CHI, and manuals on how to do it, sample data sets. Google is your pal. If you Google Reflectance Transformation Imaging or Polynomial Texture Mapping, you will get lots and lots of links to useful sites. And image search in particular will bring up all kinds of cool photos and videos showing various applications of the technique on different kinds of artifacts and surfaces. I picked at their site, rtimage.us. It's got a PDF of all the slides for this talk. There's the extended video version of this talk, which you're watching right now. There are links to other sites and documents with information about RTI. There are a number of RTI lithics data files that you can download and play with using the free viewing software available from Cultural Heritage Imaging. There are 3D model views, including some downloadable models that you can take a look at. And then hopefully at some point in the not too distant future, I'm going to put up information on how you can build your own RTI system. I'd like to say that if I can build a system without instructions, then there are lots of people who can easily build one with instructions. Finally, I'd like to acknowledge a number of organizations and individuals that have helped either directly or indirectly in the work I've been doing and in this presentation. That's it.